Hello friends, welcome back to Rising Mathematics. In this video, we are going to prove this theorem which states that if a function f is differentiable at point t in set t to the power k, then the function f is also continuous at point t. That is, every delta differentiable function is also continuous. We will start our proof. Assume that f is a function which is differentiable at point t in set t to the power k. And let us consider epsilon, which is arbitrarily chosen from the interval 0 and 1. And from this epsilon, we are going to form epsilon star as epsilon divided by 1 plus modulus of f delta t plus 2 times mu t. Here mu is the graininess function which is defined as sigma t minus t. Now since a function f is differentiable at point t, there will exist a neighborhood, say u of point t, such that for every s belonging to the intersection of the neighborhood u with the interval t minus epsilon star comma t plus epsilon star, we have the condition modulus of f of sigma t minus f of s minus f delta t multiplied by sigma t minus s is less than or equal to epsilon star multiplied by modulus of sigma t minus s. Note that since f is differentiable, so this condition is true for every point s in the neighborhood u. But in that condition, we will replace this epsilon star with epsilon. So here we are going to consider particular condition for the epsilon star which we have defined. So since f is differentiable, we get this condition. Now moving further, we have modulus of f of t minus f of s. So here we will add f of sigma t and subtract f of sigma t, and also we will add and subtract the term f delta t multiplied by sigma t minus s. So we get this whole term. Again this will be less than or equal to modulus of f of sigma t minus f of s minus f delta t multiplied by sigma t minus s plus modulus of f of sigma t minus f of t minus f delta t multiplied by sigma t minus t. So we get this term. Again observe this term. So this is less than or equal to epsilon star multiplied by sigma t minus s, which is true from here. And in the remaining term, we will do some adjustment. So here f of sigma t minus f of t as it is minus f delta t will remain as it is, and we will add and subtract t here. So we get this whole term. Again this is equal to epsilon star multiplied by sigma t minus s as it is plus modulus of f of sigma t minus f of t minus f delta t multiplied by sigma t minus t plus f delta t multiplied by s minus t. So what we have done here, we have taken these two terms as separate terms, and from this second term we have taken minus outside. So that minus and this minus will become plus, and this will be plus of f delta t multiplied by s minus t. So we have multiplied this f delta t to this both terms by taking minus from here. So we get this whole term. Again this will be less than or equal to epsilon star multiplied by sigma t minus s plus f of sigma t minus f of t minus f delta t multiplied by sigma t minus t its modulus plus modulus of f delta t multiplied by s minus t. Now this term is less than or equal to epsilon star multiplied by sigma t minus s its modulus plus, observe this term. So this will be less than or equal to epsilon star multiplied by sigma t minus t, because we know that this condition is true for every point s in this set. So clearly t is a member of this set. Since t is in this neighborhood and t is in this interval, so t will be in their intersection. So in particular, if we consider s equal to t, so this is also true. So replacing s with t, we get this is less than or equal to epsilon star multiplied by sigma t minus t. So we have used that fact here. So this will be less than or equal to epsilon star multiplied by modulus of sigma t minus t plus. Now observe that modulus of f delta t we have taken as it is, and this mod s minus t will be less than or equal to epsilon star. Since s belonging to interval t minus epsilon star and t plus epsilon star, so distance between t and s will be strictly less than or epsilon star. So we get this whole term. Now again we can take epsilon star common. So we get this modulus of sigma t minus s plus mu t plus modulus of f delta t. Now we have replaced this sigma t minus t by mu t by definition of Greeningness function. Now in the next step we will add and subtract t here. So we get this term. Again if we separate modulus we get this term. Now further we have sigma t minus t is mu t and this mu t. So this 2 will get add to 2 mu t and modulus of t minus s and modulus of f delta t we have taken as it is. So we get this term. Now note that modulus of t minus s is strictly less than epsilon star because of the same reason, since s is in this neighborhood. So distance between s and t or distance between t and s will be strictly less than epsilon star. So we get this term. Now note that we have formed epsilon star using epsilon which is chosen from the interval 0 and 1. So this epsilon will be strictly less than 1. So here we have replaced this epsilon with 1. So this term will be less than or equal to epsilon star multiplied by 1 plus 2 mu t plus modulus of f delta t. Now this whole term is less than epsilon from here. So if we multiply this new denominator with epsilon star, we will get epsilon equal to product of these two terms. So we get modulus of f of t minus f of s is less than or equal to epsilon, which is arbitrarily chosen real number from the interval 0 and 1. So we can make this epsilon as small as we want, and therefore we have f of t tends to f of s. So we can make this thing, and therefore f of t is a continuous function provided f of t is also delta differentiable at a point t in set t to the power k, and this completes our proof.